Hi, welcome to chapter number 5. We will talk today about stereochemistry and tetrahedral centers. Again, this is a support for your study. It's not in replacement of the live lectures. It's a summary of the lecture. What we'll talk today is enantiomers at the tetrahedron carbon, the reason for headedness in molecules, chirality, optical activity, Pasteur's discovery of enantiomers, sequence rules for specifying configuration, diastereomers, mesocompounds, and we will do at the end a review of isomersins. Okay, why chirality is important? Well, many drugs, I will say almost all drugs, and almost all the molecules in our bodies, amino acids, carbohydrates, nucleic acids, and many more, are handed. That means are chiral. The precise interactions between enzymes and their substrates, what is called the key and the lock, are as a result of this chirality. Basically, chirality is how is the shape in 3 dimensions. Okay, remember that our 2 hands are one mirror image of the other, but we cannot superimpose the hands. Okay, that means each one has a 3D shape determined. And precisely this is what is playing with the key and the lock. The complementarity of 2 substrates in order to interlock to create new reactions, etc. Okay, first we will define the enantiomers and the tetrahedron carbon. Molecules that are not identical to their mirror image are kinds of stereoisomers, called enantiomers. Okay, here you can see one example. We have here this monosubstituted carbon. That means, and if we draw both image, we saw that we have the same image side to side. If we have 2 different substituents, exactly the same. We have the same mirror image. If we have 3 different substituents, also the same. We always have that both mirror images are exactly the same compound. Okay. However, what happens if we are using a carbon that has 4 different substituents? For example, this lactic acid. We have a carbon that is bonded to a hydrogen, is bonded to a carboxylic acid, is bonded to a methyl, and is bonded to a OH. If we take this molecule and we do the mirror image, that means we started with plus lactic acid and we get the minus lactic acid, you can see, you can cry at home, you can cry as much as you want, that you cannot superimpose the minus lactic acid and the plus lactic acid. Never you will get a coincidence. Okay, that means a tetrahedral carbon with the 4 different substituents different will be chiral, will rise to enantiomers. A molecule that is not identical to its mirror image is said to be chiral. A molecule is not chiral if it has planes of symmetry. This is an easy way to see if one molecule is chiral or not. Okay, if we have a symmetry plane in the molecule, for example here we have a symmetry plane, we can divide this molecule in 2 and this side is the same. This is not chiral. However, here, if we do the same, we are transforming a hydrogen in OH. That means that's not possible, that is chiral. Okay? That means the no presence or the absence of planes of symmetry allow us to think that the molecule could be chiral. The best thing to do it at this level, check if you have 4 different substituents. If you have 4 different substituents, the possibility that it's chiral is very high. Okay? We will define achiral, chirality centers, stereocenters, and asymmetric center, stereogenic center. Okay? take a look at this molecule. This molecule, this molecule, as you can see here, we have the carbon in the middle, a hydrogen, a bromide, and then we have 1, 2, 3, 4 blue carbons in one side and 5 red carbons in the other side. Obviously, we have 4 different substituents in this carbon. This molecule then is chiral. Yeah? We have one chirality center. Which chirality center? This carbon. Also, this chirality center can be called a stereo center, asymmetric center, or a stereogenic center. Both are synonyms, more or less. Okay? We can take a look of this molecule. This molecule is a cyclohexane that we have a substitution in the 1 position. This is chiral? Obviously not. Why not? Because we have a plane of symmetry that converts one in the other. That means this molecule is not chiral. However, if we put a carbonyl group here, we are breaking the symmetry. That means that this side now is different than this other side, and the molecule becomes chiral. Okay? When we grow a molecule, remember that normally we don't grow the hydrogen, but we have to put the hydrogen. For example, in carbon, this molecule, this position is chiral because we have 4 substituents. It's missing this hydrogen. Okay, remember that we have to put the hydrogens. Or here, in these 3 carbons, sorry, all are chiral because we have to put the hydrogen that is missing, and then we will have 4 different substituents. Okay, remember this. What is the optical activity? Well, 2 enantiomers have exactly the same physical properties. That means if we have plus acid lactic and minus acid lactic, the boiling point for both compounds, for both enantiomers, will be the same, the melting point will be the same, everything will be the same. The only that is different is how they react or how they interact with the polarized light. What it's doing is that we are irradiating with polarized light a solution with a 1 enantiomer. This enantiomer is able to rotate the polarized light in one direction. 1 enantiomer will do it in one direction, for example right. The other enantiomer will do it in the same intensity, but on the other direction, for example left. Okay, and we have some methods, some machines, as you can see here, a polarimeter, to analyze this rotation of the polarized light. This is the only difference between 2 optical active molecules. One will be level rotatory. For example, if we take morphine, minus morphine is level rotatory, and for example, sucrose, a sugar, is dextrorotatory. That means also doesn't mean that always are rotating the natural products are always rotating the light in the same direction. That's not true. It's depending on a lot of things. Okay, that means the only that we can say is that 1 enantiomer, if the minus morphine is level rotatory, the plus morphine will be dextrorotatory. The other enantiomer of the morphine will be the opposite. In order to make easy all these numbers, we make a definition of a scientific rotation, a specific rotation, sorry, that the specific rotation is the rotation associated to one compound using normally as a polarized light, the sodium D line to measure it. Here you have the formula, and it's quite useful to identify molecules. Okay, here you have some specific rotation of some organic molecules. For example, penicillin 5 is plus 233, sucrose plus 66, camphor plus 44, chloroform 0. This doesn't have to surprise us because it's achiral, cannot rotate the polarized light. Cholesterol minus 31, morphine minus 132, cocaine minus 16, acetic acid 0. Again, acetic acid is not chiral. Then how was the discovery of the enantiomers? Well, the truth is that Louis Pasteur, a French scientist, he was doing some experiments with ammonium tartrate. Okay? And he began to crystallize to get crystals of ammonium tartrate. When he was doing the crystal of this molecule, as you can see here, he get two types of crystals. And formally, he was not expecting this. He was expecting to have only one crystal, but well, he got two types of crystals. That one was the mirror image of the other, as you can see. This means that this crystal is made, for example, with one enantiomer of the tartrate, and this crystal is made by the other enantiomer of the tartrate. This is normal, not so much, but means he was very lucky that in this case the two enantiomers crystallize in different forms. Crystallize in different crystals. That means it's more stable the homocrystal with all the molecules with the same enantiomer than not the heterocrystal. Normally it's the opposite. Okay, then well, now what we need to do is to develop a method in order to how to name these chiral centers. In order to do this, what we will do is to follow several rules. Okay? The rule 1 is always the same, is look at the atoms directly attached to the chirality center and rank them according to atomic number. We are following the Kahn-Ingold Prelog rules that we explained it for simple carbons. Okay. Always the most important will be the atomic weight of the atom, not how big is the molecule, the atomic weight of the atom. Okay. That means the ranking for the most common atoms that we can have in a molecule is bromine, better than chloride, is heavier than chloride, sulfur. Basically we follow the periodic table. Okay, this is to make the numeration. If the first atom is not enough, that means we have, for example, 2 carbons, we check to the third atom, or to the second, or the third, or the fourth. We are following the structure until we saw some difference, and again, the heavier atom always will win. Okay? Rule number 2. Okay, here is the example. We have a carbon, hydrogen, 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 or a carbon, carbon, hydrogen, 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 hydrogen. Well, in this case, this substituent will be carbon at the first, grow. Then we go to the second atom. Second atom, here is a carbon, here is a hydrogen. This will have priority. Here the same. We have alcohol and here we have ether. Alcohol, oxygen, oxygen, agro. We go for the next atom, hydrogen, and here we have a carbon. That means that this wins. Here we have carbon, 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 and here we have carbon, carbon. Again, one carbon, carbon, it's agro. Second carbon, carbon is agro, but here we have another carbon. That means that this will be heavier. And finally we have carbon, nitrogen, carbon, And here we have carbon chloride. First, carbon agro. Second, carbon nitrogen or carbon chloride. Chloride wins. Sorry, chloride wins. That means this is the higher priority. Rule number 3. Well, if there are multiple bonded atoms are equivalent to the same number of single bonded atoms, that means, I imagine that we have a carbon double bond oxygen as a substituent. This counts the same that if we have a carbon bonded to 2 oxygens. If we have a triple bond, this carbon will be exactly the same that if a carbon bonded to 3 different carbons, etc. Okay? Always by how heavy is the atom. Once we have this, the only that we need to do is to follow the sequence. My recommendation. We always saw the molecule through the carbon with the lowest possible priority. That means if we saw this, the carbon with the lowest priority is this, C4. Okay? That means we put our eye or here to see through this bond, or here to see through this bond. I imagine that we put it here. If we put it here, what we saw is 1, 2, 3. This is the rotation. The rotation is clockwise. Clockwise always will be R configuration. We say that it's a R configuration. If we have the enantiomer, I imagine, okay, we put our eye in the same position, and then we have 1, 2, 3. Okay, if we saw from this point, we saw the wheel 1, 2, 3. That means that now is counterclockwise S configuration. We can do exactly the same with the lactic acid. We have lactic acid, that is this molecule. We can put our eye here, and we saw through this carbon hydrogen bond that is the lower configuration, is the lower priority. Pam! We saw 1, 2, 3 is clockwise R. If we check the enantiomer, 1, 2, 3, anti-clockwise S. Okay? Please try to do problem 5.10 at home. If you have any problem, send me an email or check the tutorials that we did about stereoselectivity. Okay, what happens if, for example, I am lazy and I put the eye just opposite? If the hydrogen is close to my eyes instead to be far away of my eye. If the hydrogen is going to my eye, I put the eye here. What I have to do is exactly the same that I did, but at the end, what is R will become S, and what is S will become R. Okay, only for this. Check the tutorials, and there is, in these tutorials, it's very well explained. What are diastereomers? Well, when we have 2 or more chiral centers in a molecule, okay, what we have, if we have 2 at the number of stereocenters as stereoisomers, we have this number of stereoisomers. Okay, here, for example, we have a compound that has 2 chiral centers. we can grow these different products. The 2R free R, the 2S free S, the 2R free S, and the 2S free R. Okay. You can say that this and these two first, the 2R free R, 2S free S, are enantiomers one to the other, and the 2R free S and the 2S free R are enantiomers one to the other. However, if we have at least one chiral center with the same configuration in one molecule and one chiral center with different configuration, what we have is called diastereomers. Are stereoisomers that are not mirror image. Okay, that means again, diastereomers are compounds that has at least two chiral centers. They can have infinite, but at least two. One of them has to be, at least one of them has to be the same, and one of them at least has to be different. Okay, it's the only rule to be diastereomers. Good. What is a mesocompound? A mesocompound basically is a compound that looks like chiral, but it's not chiral. For example, we have this compound. Okay, 2R free R and 2S free S. Or we have this compound, the 2R free S, 2S free R. In one of them, in one of them here, we have a plane of symmetry. Okay, here, dividing this molecule, we have a plane of symmetry. That means this looks chiral because this carbon and this carbon has 4 substituents different, but because we have a plane of symmetry in the molecule, simply this compound is not chiral, it's achiral. When we have compound that has chirality centers and symmetry planes, are called mesocompounds. Okay? Then finally we can do a review of isomerisms. Okay, remember that we started with isomers. What means constitutional isomers? Constitutional isomers are compounds that has the same molecular formula, but they are built, they are constructed, the bond, the matrix of the bonds is different. For example, we can have ethanol, CH3, CH2OH, or we can have dimethyl ether, CH3, oxygen, CH3. Both have the same formula, but the construction is different. These are constitutional isomers. If the bonding is the same, then we have stereoisomers. That could be enantiomers if one compound and the other, one is the mirror image of one is the mirror image of the other, but are not superimposable. Or they can be diastereomers when we have 2 or more chiral centers with at least one chiral center is the same and at least one chiral center is different. Okay, also we can have configurational diastereomers, that is what I said. And also we have to remember that we can have diastereomers that are cis-trans. Okay, for example, when we have 2 substituents in a ring, both can be in the same phase or both can be in different phases. This is cis-trans. These are also diastereomers. In the case of EZ, it's exactly the same. Double bonds E and Z, cis-trans, are diastereomers. Okay, here you have examples of constitutional isomers, what I explained. The bonding is not the same for all. Stereoisomers, the first example are enantiomers, the second are configurational diastereomers, okay, because they have one chiral center that is the same and one chiral center that is opposite. And finally, we have cis-crans, in this case, a ring where the two substituents are in the same direction, in the same side, in the same phase, or in different phase. Same phase, different phase. Okay, please, you have the study questions here for problem solving sessions, reading assignment, etc. Thank you very much for your attention. If you have any question, feel free to send me an email. I will be more than happy to answer.